Okay, so thank you very much. So welcome to probably our last leg of class. See how we can finish this. All right. So see, as promised, we're going to come back to this example 411. See, it says here, draw the board diagram for the following transfer function. But we are not going to compute every point like we did before. We are going to draw using the straight line approximation. And then we're going to use that to help us quickly draw the board diagram by straight line approximation. So I have also uploaded this note to your e-learning. So this is now a supplement notes, yes. So this is example 411. So we want to draw the board diagram for just a transfer function just equal to constant k. So now your magnitude is not a function of omega. So if you substitute j is equal to omega, it's still going to be k. So the magnitude k is just a pure real number. So the magnitude of k is not going to change as a function of omega. It is just a constant. So the decibel is also not going to change because it is a constant, 20 log k, not 20 log of as a function of omega. So this is just a constant. And the phase angle of a pure real number is just 0. So now, so this is now, your magnitude is just a constant line, constant horizontal line, and the value depending on the value of k, 20 log k, whatever k is. If k is equal to 2, this is 20 log 2. If k is equal to 5, this is 20 log 5. It is just a straight line, just like that. And the phase angle is always 0. So if you have a term in your, if you have a constant term in your transfer function, all you have to do is add this line to your curve, this horizontal line, and the phase angle is equal to 0. So that is quite simple, right? This is why I call the straight line approximation. And then let's go to part B. So now let's say you have a term of your transfer function is equal to S. Now substitute S equal to j omega. And the magnitude is going to be equal to omega. Square root of omega squared is going to be omega. And now the decibel is 20 log that. So you have 20 log omega. So this is now a pure imaginary number. Pure imaginary number, the phase angle is always positive 90 degrees. So this is a phase angle. So the phase angle is a constant. So if you draw the phase angle, it is just, it is not a function of omega. It's just a constant 90 degrees. But now suddenly here, so your decibel now will depend on the value of omega. So let's say example, omega is equal to 1, log 1 is 0. So 20 log 1 is 0, so you get that point. And then you substitute 10, log 10 is 2, is 1, log 10 is 1. 1 multiplied by 20 is 20, so you get 20 there. So at frequency 10, you get decibel is 20. At frequency 0.1, you get here negative 1. Negative 1 multiplied by 20, you get negative 20. So basically, you get that straight line for the decibel curve. It will go through point. So 0 decibel happen at omega is equal to 1. When omega is equal to 1, the decibel is 0. But this is just a straight line with a slope of 20 decibel per decade. So this is 1 decade. From 1 to 10, there's 1 decade. 10 to 100, there's another decade. So the slope is just a positive 20 decibel per decade. So every time you have that term S, so you add this curve to your the total line, and then you have the influence of S is just that line. So you add this, so you can add that to your total curve. Okay, what happens if 1 over S? So again, substitute S equals j omega. So it is just 1 over j omega. So the magnitude is 1 divided by square root of omega squared is 1 over omega. So the decibel is 20 log 1 over omega. And now, if you still remember your mathematics from your middle school, so 20 log 1 over omega is just negative log omega. So this is fundamental of logarithm of logarithm. So negative 20 log omega. And then the phase angle of 1 over j omega, it is always negative 180 because the term is in the denominator. I mean negative 90. So the phase angle is constant, negative 90 for 1 over s. But now suddenly your decibel is still when omega is equal to 1. So the decibel is still 0, log 1 is 0, multiply negative 20 is still 0. But now this straight line here is now at a curve, at the slope of negative 20 decibel per decade. Negative decibel per decade. If you have 1 over s squared, the slope is going to be negative 40 decibel per decade. It's still going to go through that point, omega equal 1. It's going to be still 0 decibel and omega equal 1, but the slope is going to be negative 40 if your term is 1 over s squared. So now this is how you draw the Bode diagram using straight line approximation. And then you're going to have this first order transfer function 1 over 1 plus ts, and then you're going to have this second order transfer function. So basically, again, just for first order transfer function, substitute s with j omega, and then you have this magnitude, square root of the real part square plus the imaginary part square, and then the decibel is 20 log that. Again, since this is in the denominator, so you put a minus sign and then flip the ratio over. So this is your decibel curve. And then your phase angle is, since this is, you have the real part, you have the imaginary part. So the negative sign comes from the fact that your term is in the denominator. And then since your real part is just 1, so the imaginary part divided by 1 is just the imaginary part. So this is your phase angle. All right, but you can see that the value of decibel for small value of omega, see, for small value of omega, 1 plus a small value, so that term is negligible compared to 1. For small value of omega, you square that, and it is negligible compared to 1. Again, square root of 1 is 1, log 1 is 0, so the value of decibel is going to be 0 for small value of omega. And then for large value of omega, when omega is large, 1 is now negligible compared to that. For example, omega is equal to 100, omega is equal to 1000, 1000 square plus 1, so 1 is negligible. Okay, so you just drop that one. So all you have is that negative 20 log d omega for large omega. And then, so this is how we cheat. Okay, we say that for small value, that's 0, okay, 0. And then it's going to drop by negative 20 per decibel, and negative 20 decibel per decade when you reach this break frequency. So the break frequency is 1 over t. See, 1 over t, when omega equal 1 over t, so this is t multiplied by 1 over t, this is going to be 1, so this 1 plus 1, basically we just approximate the whole thing as 1. So you have two straight line, 0 for frequency small, and then this is the break frequency. It's going to drop at 20 decibel per decade when you reach this 1 over t. T is your time constant, and your phase angle at 1 over t, when omega equal 1 over t, so this is t multiplied by 1 over t is 1, arctangent of 1 is 45 degrees, so that's your 45 degrees. When omega is 0, phase angle is 0. When omega is large, this is going to be very large, so the phase angle is negative 90. So that is your phase angle, 45 degrees at the break frequency. Break frequency is 1 over t, and then it's going to go from 0 to minus 90 degrees. So this is, you can approximate the Bode diagram for first order term using that 0, and then you drop by negative 20 per decade at your break frequency. And then you can use the same argument for second order. For second order term, you can translate this into that expression. And of course, you use the same argument for small omega, for large omega. For small omega, you have 0, and your break frequency is at omega n. After omega n, you're going to drop by negative 40 decibel per decade. And then your phase angle is going to be negative 90 at omega equal omega n, and it's going to start from 0 to negative 180. So every time you have this second order term, you can approximate your Booth diagram using these two lines. Okay, one for phase angle, one is for the decibel. Okay, so normally we will not have this just simple term. Normally we will have a combination of term like K, 1 over S, 1 over plus TS, a combination of that. If you have a combination of the term, all you have to do is add these lines together to get your resultant of a Booth diagram curve. For that, we are going to look at example, what? I don't know, I can't remember. Well, this is too simple. All right, so let's take a look at this example 415. How we can get the resultant Booth diagram from this, if our transfer function is 10 divided by s plus 2. Okay, I have an example for that. Okay, so let's go here. All right, so this is example 4.15. So this is our transfer function, and then we can decompose that into these three terms. We have 5, 1 over s, 1 divided by 0.5 plus 1. Okay, so this is the original transfer function. So we can see that this transfer function can be written in these three terms. So this is just k. So we know how to draw a Booth diagram for a constant k. We know how to draw a Booth diagram for 1 over s. We know how to draw a Booth diagram for 1 over 1 plus ts. And then we just add those three curves together. That's it. And then you have your Booth diagram. So let us do that. So let us now, okay, by the way, so this is your, this is my mistake. Ignore this line here. This is a mistake. So I already crossed that. Okay, so this is a mistake. So this is your semi-log graph paper, how semi-log graph paper looks like. Okay, how semi-log graph paper looks like. So we have three curves. K is equal to 5, 1 over s, 1 divided by 0.5 s plus 1. So this is our time constant, 0.5. So okay, so now let us prepare the axis first. So you're going to learn how to prepare your axis when you draw your Booth diagram. So the light blue here is the axis. Okay. So here I have 3 cycles. So this is 1, frequency 1, frequency 10, frequency 100. Every decade you multiply by 10. And the frequency here is not 0. 0, this is a 0 decibel, the vertical axis. Vertical axis here is 0 decibel, but the value of frequency here is not 0, it is 0.1. So 1 decade to your left, you divide it by 10. So divided by 10, so that is 0.1. So the horizontal axis is your frequency axis, start from 0.1, 1, 10, 100. You use the same scale for phase angle, 0.1, 1, 10, 100. All right, so we have these three terms. So this is 5. So 20 log 5 is that. So this is the green line here is 20 log 5. Is about 14 decibel. Okay, so that's your first line. So the phase angle for a constant k is just 0. So you have that 0, the green line there, there's 0. It's not going to affect your phase angle. So this is 20 log 5. Your second term is 1 over s. So 1 over s, you have this line. This is 1 over S. It's going to go through 1.0, and it's going to drop at negative 20 decibel per decade. So from 20, drop by 20 decibel, drop another 20 decibel. And the phase angle for 1 over S is always negative 90. So this is negative 90. This is another green line there. It's negative 90. So this is for 1 over S. All right, so now your last term here is 1 divided by 0.5S plus 1. So this, your break frequency is 1 over 0.5. Your time constant is 0.5. 1 over 0.5 is 2. So you go there, so you find 2. So this is 1, that is 2. So this is frequency is equal to 2. That vertical line is frequency is equal to 2. It is not linear. This is 2, this is 3, there's 4, there's 5, right? So this is your break frequency. So you have 0, and then when you hit the break frequency, you're going to drop by negative 20 decibel per decade. So this is your third line. So you have 3 green lines there. And all you have to do is add those 3 green lines to get this is the resultant, the red line. The red line is your resultant Bode diagram. Okay. And then the phase angle for this first order term is going to be 45 degrees at 1 over t. 1 over t is 2. Our time constant is 0.5. 1 over 0.5 is 2. So 45 degrees when frequency is equal to 2. So this is your curve. This is your phase angle curve for your last term. And then all you have to do, you must add these 3 lines together. So you add those green line together, get your resultant magnitude. And you add these 3 lines together, 3 green line of phase angle together to get this resultant curve. You just add them. How do you add? So 0 plus 0 plus 0, 0 plus 0 minus 90, you get 90, negative 90. Again, that's 0 minus 45 minus 90. So that's minus what? So 135. 135 there. And there is 0 plus 90 plus 0 minus 90 minus 90 is minus 180. So you plus that. So the curve here is also, you can add point by point, or you can add the slope. So the slope here is negative 20, but that point is, of course, that's 0 plus 14 plus 20. So this is 34, and then you go down by negative 20 per decade until you hit, and then you must add another line when you hit the break frequency, and then the slope is going down by negative 40 decibel per decade. So that's how you draw the Bode diagram using straight line approximation. I do not recommend you do this in your test, but it is also accepted if you do this in your test or final exam. Okay, the more term you have, let's say you have another term, you're going to have another green line, and then you need to add that to your resultant curve there. Just add those lines together. Any question? I'm glad that I have this semi-log graph here. Okay. All right. No question is good. Okay. So now we come to this this question. Final example. Okay. Approximate the transfer function from the frequency response data. So I have put some guideline here. You can estimate the Bode diagram from the Bode diagram. So there are a few steps that you have to go through here. Approximate using a straight line, and then the value of the frequency where the slope curve is the break frequency. Okay. Every time you go down by negative 20 decibel per decade, there's a time constant there. You can get the time constant there. But this is a very simple transfer function. So all you have to do is Now you need, before you draw your book diagram, so you need to convert this into decibel. So let's go to my notes. Okay. So your first task is, of course, to convert this magnitude into decibel. 20 log G, 20 log magnitude of G. So 20 log 199, 20 log 12, you get 21.6, 20 log 2, 20 log 0.5, and so this is your point. Now you need to transfer this point. So this is your frequency, 0.1, 0.4, 1, 2, 4, 6, 8. Okay, you need to prepare your axis. You only need 2 cycles here. Okay, now take a look at my frequency. So this is there is 1, there is 10, there's 100. So the value of frequency here is 0.1. Okay, so your first point, frequency 0.1 at 46 decibel. 46 decibel is 20 log 199. 20 log 199, you get 46. Frequency 0.1. So this is 0.1. So that's 46. So this is a vertical axis. 0 decibel, 20, 40, negative 20, negative 40. And then you transfer the rest of your point. For example, at frequency 2, negative 6 decibel. So where's your 2? So this is 2. There's 1, there's 2. So that's negative 6. Last point, that's 8, frequency 8, 43, negative 43 decibel. So, so that's 0.1, 0.2, 0.3, 4, 5, 6, 7, 8. So this is frequency 8, that's frequency 9, that's frequency 10. So this is frequency 8, frequency equal 8, decibel, negative 43 decibel. So you go down, there's 40 decibel, there's 43 decibel. At frequency equal 8, your decibel is 43. Now with all that point, you need to approximate using straight line. So the first line, I have this, the first line join I join these 3 points together as a straight line up to the 4th point. So the slope here is negative 40 decibel. And then here, join these 3 points together as a straight line, you get the slope of negative decibel per decade. You can see this is negative 40 decibel per decade, so this is negative 60 decibel per decade. Now you need to ask a question, what is the format of transfer function that will give you this type of curve? Okay. So negative 40, you can get negative 40 from 1 over s squared. So 1 over s squared will go through that 40 and then 0, negative 40 decibel per decade. But you raise the curve by some 6 decibel. So you're going to have a constant of 20 log k being equal to 6. And then, so this is your break frequency where the slope changes from negative 40 to negative 60 decibel. There's one time constant there. So the break frequency is equal to 2. Your time constant is going to be 1 over 2, which is 0.5. So the general term, so if your transfer function is in this format, generally you are going to get this type of curve. Okay, you have k. S squared is going to give you this negative 40 decibel per decade. So 1 over 1 plus ts is going to add another negative 20 decibel per decade. So you're going to drop, after dropping negative 20 decibel per decade, you're going to drop another negative 60 decibel per decade. So this type of transfer function will give you this form of decibel curve. All you have to do now, what is the value of k? What is the value of this time constant? So k here is just that. So 6 decibel. So the total curve is raised by 6 decibel. So 6 decibel is equal to 20 log K. So you have K is approximately equal to 2. And your time constant here is 1 over break frequency. So break frequency is equal to 2. Therefore, your time constant is equal to 0.5. So you can extract the transfer function that will generate this Bode diagram curve is that we have 2 divided by S multiplied by 1 plus 0.5 S. So this is your, you can extract this transfer function. If you are not confident enough, you must reverse back and you must, given this transfer function, you know that you can get, you can now compute the point. Do you get that point back with this transfer function? Of the substitute S with 0.1 omega, substitute S with 1 omega, and do you get back the magnitude? Do the reverse process, and I'm going to leave that to you as an exercise to double check whether this transfer function will generate this curve or not. But again, this is just a supplementary note. This is just additional to our discussion. Probably is not going to be asked in your final exam. But there is a chance that it's going to be asked. It is, I can take 10 to 1 odd, I guess. Okay, so that's it. So that's the end of our class. So we have covered everything. We have covered everything that we need to cover in this basic control engineering course. Do you have any question? This is going to be our last class. We are not going to have any more classes after this. This is goodbye. Okay. If you have any question, then you can always reach me in the WhatsApp group if you have any question. Make sure that you complete the assignment, your 4th assignment, and that's about it. Your final exam, are we covered all? Yes, that's all. That's all. We have covered all. Your final exam is going to be 4 questions. Okay. First question is on mathematical modeling, chapter 1. Second question is time response of probably second order system. That's the second question. Your third question is just going to be 4 questions in the final. Third question is stability and root locus diagram. And then the final question on your final exam is frequency response on this Bode diagram. There's a question on the chat box. What chapter on test 2? Test 2 is going to have 2 questions. One question on stability and root locus interpretation. Second question is frequency response analysis up to Nyquist diagram only. Bode diagram will not be asked in your second test. So second test is going to cover only Nyquist diagram. All right. Any more questions? All right. So, okay. See, this is a problem with control engineering. There are 500 of you. There's only one lecturer is going to mark all 500. So one of the lecturer has not finished mark, I think, question 1. So again, we cannot tell you the mark for your first test because it's only one lecturer is working on it. See, I'll be marking your second question of your final exam. That's on me. I'm going to mark every single student, 500 plus of them, second question of your final exam. So sorry. Then that's how the way it is. To be fair for all students, so that the grading is uniform for every student. So one lecturer is going to mark one question from the test, and sadly that's going to take a long time. You are not going to see your marks. I'm so sorry about that. All right, so if you have any question, you can raise your question in our WhatsApp chat group. I'm going to stop my presentation here. So I guess I'll see you around. Thank you, everybody. This is the end. So bye-bye, goodbye. Okay, so there is a question. What is that? Okay, this is just a thank you. Okay, I'm cool. Thank you very much.